Did I start the right meeting? Did I post that to the wrong place? Okay, just take a second. All righty, I see folks are starting to trickle in. Welcome, guys. Sorry for the late post. Today, we are going to pick up where we left off last time. Last time, we kind of introduced min-max problems and the idea of an absolute min and absolute max for continuous functions on closed bounded intervals. I do have some news regarding your tests and some stuff to share with you about that. Some of you, your tests were graded, which is awesome. I am still struggling with some technology issues, and because this has been such a pain in the ass, I feel obligated to at least show you. So I'm going to take 10 seconds here to just, I promise you, verify what's going on, because I understand if it's getting frustrating on your end. So let me go ahead and turn on the screen share. We can get started. Here we go. So this is MAC2311, section number 004, which is Calc 1. The date today is the 21st of February, 2022. And today, we're going to do a few things. We're going to talk about min-max problems, which is section 4.1. And then we're going to talk a little bit about increasing, decreasing, and the connections to local extrema, which is something from section 4.2. There is other stuff in section 4.2 that we probably will not get to today, but this is my plan at least. And then if we're moving at a good speed and everybody feels comfortable, then I'll continue a little deeper into 4.2. But before I get there, first, I do want to apologize to those people whose tests have not been graded yet. I know this is deeply frustrating on your end, and as a kind of show of good faith, I wanted to show you what it is I'm struggling with. So the way I grade your tests is by looking at your written work, which you submit to an assignment titled Exam 1 Written Work, obviously. And then I pop that open, and I can look at what you've done. I'm not going to pop it here because it's going to go to the first one, which may or may not display. But I wanted to show you, here is what I'm dealing with, right? So as I go in and work on this stuff, usually for 30 or so minutes, everything will work fine. And then when I pull up the next one, whether I'm doing it on my browser or my iPad here, I get this error and I can't see the damn work. So I'm going in and working on your stuff and I get a couple done, and then this happens and it takes a few hours to resolve, and it doesn't seem like there's anything I can do or Santa Fe IT can do to make it work. I thought it was a problem with the iPad at first, but then I switched over here and started typing comments and started getting the error here. So I promise you I'm working on this. One little option here, if you are starting to feel stressed out about not having your exam grade, which I totally understand, go ahead and email me the work. Because for whatever reason, I can't access it through Canvas right now. If you email it to me, I won't be able to annotate it like I would on the iPad, but at least I'll be able to get your scores in. And I know you guys want that. So if you're in that position where things you're starting to have a hard time feeling where you're at in the class because you don't have that grade yet, if you email me the work, I will grade it based on what you email me. I will, of course, once I'm able to look at it in Canvas, check and match it up and make sure it's the same. So please don't add or remove anything in what you email me. But that way I'll be able to look at it and enter your scores, and we can start moving forwards with that. So that said, let's return to where we were on Friday when we did a little bit more linear approximation stuff, but then we spent the bulk of the day kind of going through the theory behind these min-max problems with a focus on the absolute min and absolute max of a continuous function on a closed bounded interval. So if you take a function that is continuous and maybe its natural domain is a closed bounded interval, or maybe it's continuous on some larger set, but you restrict it to a closed bounded interval, we had this theorem called the extreme value theorem. And this says if f, all right, I'll say f of x is continuous on the closed bounded interval AB, right, meaning it doesn't go off to infinity and includes both endpoints, right, written with brackets, then f of x attains both an absolute max, I'll say min first, right, absolute min, and absolute max somewhere on that interval. So this is an existence type theorem. It guarantees the existence of something. And there, in general, in mathematics, there are kind of two main types of theorems: existence theorems and uniqueness theorems. Like this thing is out there, and here's how you get it. The uniqueness theorems are generally constructive and tell you how to get the thing. The existence theorems tell you that the thing is there. So this is a theorem that tells you, hey, if you're looking at a continuous function and you're paying attention to it only on a closed bounded interval, then on that interval, this function will attain a smallest possible value and a largest possible value. And we saw some examples the other day of how this can fail. If you have a function that's continuous, but the domain that you're considering is an open interval, then you could have like a vertical asymptote, which will keep you from having an absolute max. Or you could have something that's jumping around really weirdly in such a way that you do not attain an absolute min, like that function we had where there's an open circle at the bottom of one of the pieces. So if you break the continuity or the topology of the interval, then there's no guarantee that these things exist. But if you have a continuous function and you're paying attention to its behavior on a closed interval a to b, then both of these things will be there. The other big theorem from last time was Fermat's theorem. This was that theorem due to Pierre de Fermat. Which says if f of x is differentiable specifically at x equals c, and f, let's say f of x again, or just f, has a local min or max at x equals c, then f primed of c must be 0. So if your function has a smooth graph, specifically smooth at a local min or max, then the only possible value for the derivative at that min or max is 0. The second theorem is easy enough to illustrate, and we can try to illustrate it in the context of the first. So let me take a closed bounded interval, and I'll just draw some smooth function whose domain is this interval. And what we see here is that, yeah, there is going to be inevitably a tallest point on this graph. There is inevitably going to be a lowest point on this graph. And if those tallest point and lowest point are coming from places where the function is smooth and the interior of the interval rather than one of the endpoints, then those would also be local extrema, local mins, local maxes. And without violating the smoothness criterion, it must be the case that the tangent lines at those extrema are all horizontal. And in this case, your abs max is right here. And your absolute min is down here. Now, another possibility is that one or even both of the absolute extrema could come from an endpoint. So let me illustrate this. So again, anywhere you have a local min or max within the interior of this interval, that is away from the endpoints, because the curve is smooth, Fermat's theorem guarantees that the tangent line at those points must be horizontal. And like the previous guy, your absolute min is coming from one of these interior points. Your absolute max, though, in this case, is coming from one of the endpoints. And these two pictures pretty well wrap up the possibilities. If you flip the second picture upside down, then the absolute max would be coming from an interior point and the absolute min would be coming from an endpoint. But I would say that if you understand these pictures and how they relate to that theorem or those two theorems, then you're in pretty good shape. So all this theory is stuff we discussed on Friday. What I want to do today is give you some practice at actually finding these things. Complete the pictures with some axis labels here.
Professor, I had a question.
Yeah.
So if we were to plot like a sine graph, does that mean we would have multiple absolute mins and max, or would it only be one max and one min?
No, indeed, if you look at the graph of any sinusoid, like we can be quite general about this, you could have something like y equals 2 cos x minus pi over 4 plus 3. Anything that has a graph which is wavy like this, those things you learn how to graph in trig by stretching, shifting, and moving around, you will have infinitely many extrema. And it is the case that every one of the upper points is a local and absolute max, and every one of those lower points is a local and absolute min. So it depends on how you're phrasing the question. It's true that there can only be one absolute max value. Remember, when we talk about the value of the max, that's the y value. But it can occur, or in the language of the extreme value theorem, it can be attained infinitely many times. So here the max value, the absolute max, is 5. And it's attained at -7 pi over 4, pi over 4, 9 pi over 4, 17 pi over 4, 25 pi over 4. It shows up infinitely many times, but there's only that one absolute max value. So the y value for the absolute max can only occur once. And the same thing is true for the min. The y value for the absolute min, there can only be one smallest y value, right? If there was another one that was different, one of them would be bigger than the other. So one of them couldn't be an absolute min, but they can occur or be attained as many times as you like. Is that satisfactory?
Yep, thank you.
Cool. Yeah, okay, no problem. So if I give you a continuous function on a closed bounded interval, how do you find these things? I would like to be able to find all the points illustrated here. And I'd also like to be able to tell which of them is the absolute max and absolute min. So if you look at say the picture on the left, there's several good candidates, several good things to think about. Suppose I tell you that like this guy right here is C, this guy right here is at D, and this guy right here is at E. If I give you the numbers A, C, D, E, and B, how could you tell which one of those is the location of the absolute min? How could you tell which one of those is the location of the absolute max? Any ideas there?
You would find the values of 0.
So I think what you're getting at there is how we would find the numbers, right? C, D, and E themselves. It's true that the way we're going to discover these X values is by setting the derivative f primed equal to 0. That certainly is true. But let's imagine that I handed you these numbers. I already found them for you and I gave you them. How would you know which one corresponds to the absolute min and which one corresponds to the absolute max? And I promise, not a trick question.
Highest and lowest y values.
Yeah, what Cameron said is exactly correct. If you have these X values, you can calculate the Y values by plugging those X values into the original function. And then whichever one has the biggest Y value, that's got to be the absolute max. You see, the idea is that the absolute max must occur at one of these numbers. The only possible places for the max to occur is at one of the endpoints or one of these local extrema in between. So if you know all the possible X values where they could happen, and that's what these theorems do, they tell us all the possible values where those could happen, you can determine which one is actually your absolute max and which one is absolutely your absolute min by just plugging those X values into the original function and comparing the Y values. What this does is it prescribes an algorithm for finding the absolute min and absolute max. So this is called the closed interval method. It says to find the absolute extrema, which is again, it's just the name for mins and maxes together, for a continuous function f on the closed interval AB. First, find f prime. Second, solve f primed of x equals 0 and record those solutions. Maybe here I'll call them like x1, x2, whatever. So you have n of them, xn. Then finally, you just compare the y values on the graph at all of these points, all of these x values, and the endpoints, right? Because the, the absolute min or absolute max could also occur at one of these endpoints. So you're going to compare f of a, f of x1, f of x2, right? All of those places where the tangent line is horizontal, and f of b. The largest is the absolute max, the smallest is the absolute min. It's almost like silly, kind of how straightforward it is. But really, what these two theorems do, Fermat's theorem and the extreme value theorem, is they give you a list of possible X values where your absolute min and absolute max could occur. And then in order to figure out where the absolute min or absolute max occurs, you just test all those possible X values. It's kind of like the rational roots theorem from pre-calc, if you remember that. It's a theorem that gives you a list of all possible rational roots for a polynomial, and then you check them. Here you get a list for all the possible locations of an extrema, and you check them. Thankfully, the checking here doesn't involve anything like synthetic division. It's just plugging in. But these problems can become a little bit cumbersome depending on how nasty step 2 is. Solving f prime equals 0 can be as hard as you want because you're solving an equation. God knows that can get tricky. So let's pop up your text and look for some nice, appropriately challenging problems. Proof of Fermat's theorem is kind of cute, but not anything super special. I will define critical numbers for you. It's the closed interval method. All right, let's look at this guy. So we've got x cubed minus 3x squared plus 1, and we want to look on the closed bounded interval -1/2 to 4. Let's say find absolute extrema for f of x equals x cubed minus 3x squared plus 1 on the closed bounded interval -1/2. So following our closed interval method, we're going to take the derivative here, figure out where he is equal to 0. There's a little catch here. I'm sorry. We're not only interested in places where f prime is 0, we're also interested in places where f prime of x is undefined. I'm so sorry. Let's come back here, and generally they'll come from things like this. If your function is nicely behaved, if it is smooth, the picture will always look like this. But it is possible to have a continuous but not smooth function, and at those not smooth places, you could also end up with a min or max. Think like the absolute value function, right down there at the bottom. He's not smooth, not differentiable, but he would have an absolute min there. So I'll look at an example like this in just a second.
Could you just slide the paper a little bit down?
Down?
Yeah, or up, I mean.
Okay, yeah, sure. Here we go.
Thanks.
So again, I'm just asking in step 2, we're going to, in addition to solving f prime equals 0, we also need to solve where f prime is undefined. And then we record those solutions and compare the outputs, the y values at all of those numbers. The name, by the way, for all of these solutions, places where f primed is 0 or undefined, but f is defined, those are called critical numbers. Okay, so let's do it. I want to find all the absolute extrema for this function on this interval. This function is a polynomial, so we can trust that it is continuous and differentiable everywhere. In particular, it is continuous on this interval. So I can apply my closed interval method. F prime is not hard here. This is a polynomial, so we just apply the power rule. We get 3x squared minus 6x. F prime of x is going to be equal to 0 if and only if 3x squared minus 6x is equal to 0. And we can factor that left-hand side as 3x times x minus 2. So there are two numbers, both coming from this interval, where the derivative is equal to 0, i.e. two critical numbers. First being x equals 0, the other being x equals 2. And then we just need to compare f at the left endpoint f at the interior critical numbers, which are 0 and 2, and f at the right endpoint. Whichever one of these outputs is the smallest will be our absolute min. And by smallest, I mean smallest in the sense that we talk about on the real numbers. Negative numbers are smaller than positive numbers, right? -10 is smaller than -2. If I evaluate f, the original function at -1/2, I get -1/2 cubed minus 3 times -1/2 squared plus 1. The cube of -1/2 is -1/8 minus 3 times -1/2 squared is +1/4. So this will be -3/4. And then plus 1. If we have a common denominator here of 8, then this is -2/8. I'm sorry, -1/8, and then -6/8 plus 8/8. 1/8 is still 1/8. So that's -7/8 plus 8/8 is +1/8, or 0.125. F of 0 is 0 cubed minus 3 times 0 plus 1. That is definitely just 1. F of 2 is 2 cubed minus 3 times 2 plus 1, which is 8 minus 6 plus 1, which is 2 plus 1, which is 3. And f of 4 is 4 cubed.
Okay, I'm sorry.
Oh, yeah.
Under the one you just did, isn't 3, the second part, isn't it 2 squared?
Oh, yeah. Thank you. Sorry. Yeah, the square here didn't hurt me because I left it off of the 0. This is supposed to be 2 squared. Thank you. So that will change this. That's very kind of you. I appreciate the catch. This is going to be 8 minus 3 times 4 is minus 12 plus 1. Yeah, and that will make a difference. So that's -4 plus 1 is -3. Thank you. Okay. And then our last guy, f of 4, will be 4 cubed minus 3 times 4 squared plus 1. 4 cubed is 4 times 4 times 4 is 16 times 4 is 64. Minus 4 squared is 16. 16 times 3 is, let's see, 16 times 3 is 48. Is that right? 30 plus 3 times 8. Yeah, 48. And then plus 1 is plus 1. And then 64 minus 48 is 2 to get up to 50. And 10 to get up to 60 would be 12, plus 4 is 16, plus 1 is 17. So now we have all of our outputs. 1/8, 1, -3, and 17. So the smallest of all 3 of these will be our absolute min, and the largest of all 3 of these will be our absolute max. So we see that this is our absolute max, 17, and the smallest of all of these is -3. So this is our absolute min. Yeah, without that square, I would have missed that. So thank you. The language we would use to describe these, we would say that the absolute min is -3, and it's attained when x is equal to 2. the absolute max is 17, and it's attained when x is equal to 4. And it might seem like a trivial thing, but pay enough attention to the language that you can recognize when it's being used in subtle ways. Good source of like true false type questions, concept type questions. It's possible to understand the picture, but have the language throw you off enough to make a mistake. So we talk about location of the min or max, that's always the x value. When we talk about the min or max itself, the min value, the max value, then we're talking about the output or the y value.
A question.
Yeah, what's up?
Is it possible to get two of the same value? So like you can get two absolute mins and two absolute maxes?
Kind of depending on what you mean, maybe yes, maybe no. So if we think back to here, right, there were min absolute max occurred many, many times, but it's always the same max. So the value of the max is always 5. If there was another absolute max with a different y value, well, if you have two real numbers, one is always, and they're not equal, one is bigger than the other. So it's not possible to have two different absolute max values, right? If there was another point on this graph with a different y value that I thought was an absolute max, then that y value is either bigger than 5 or smaller than 5, right? If it's not the same, if it's not equal to 5, it's either bigger or smaller. If it's bigger, then that point is the absolute max, and these are not absolute maxes. If it was smaller, then that point's not an absolute max, and these remain the absolute maxes. So it's possible for an absolute min or absolute max to be attained multiple times, but it's not possible to have two different absolute min values. It's not possible to have two different y values that are the absolute min value. You can have many local extrema, local mins and local maxes with different y values. That's not a problem. But the absolute min is the smallest number in the range. That's the way to think of it, right? So if you think of the range of a continuous function, that will be a closed interval. That closed interval has a smallest element. The smallest element of the range is the absolute min for that function. And there can only be one of them, but it may get hit many times. And the same thing's true for the max, right? The absolute max is the largest element of the range. It may get hit many times, but there's only one largest element of the range. So no matter how many times it's attained, the absolute max value won't change. But we could, for example, here have like the absolute min is -3 and it's attained when x is 2, 0.5, blah, 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 right? That is a possibility.
Thank you.
Yeah, of course.
Actually, well, I had like one more question. So could we ever write the statement as it would be absolute min is -3 and is obtained when x is 2 and another function? Would that ever be a possibility?
So yeah, it is possible to have something like the absolute min is -3 and it is attained when x is 2 and when x is 0 and when x is 3. That is a possibility. Yep. So I like this comment enough that we can add it to the notes here. Let's say note, the following is possible. So I could have some function that does something like this. Kind of cruises all around and hits, because I've drawn it here, that wouldn't actually be the absolute min anymore, but hits your absolute max multiple times and hits your absolute min. Sneak this down a little further so it looks better. Hits your absolute min multiple times. So here your absolute min, if we pretend my art is better, and these are both on the same y value, and your absolute max right here, these are both on the same y value. If this is like 1, 2, 4, 6, then your absolute max is whatever this y value is. Let's call it 10. And your absolute min down here, 4. So here, the absolute min is 4, and it's attained when x is equal to both 2 and 6. And similarly, the absolute max is 10, and it's attained when x is equal to 1 and 4. So something like that certainly can happen. And you notice there's also lots of local extrema in here. There's a local, looks like a local max here, a local min here, local max here, which would be separate objects. But in 4.1, the goal is really just to search for absolute mins and absolute maxes. Let's try something a little more subtle. Little space telescope. I guess we'll work the trig example here. There's nothing wrong with that. Always need more practice with this. So how about x minus 2 sine x on 0 to 2 pi? Let's say find all local, or find all absolute extrema, sorry. F of x equals x minus 2 sine x on the interval 0 to 2 pi. And again, we're going to use the closed interval method, right? X is a polynomial function, so it's continuous. Sine x we know is continuous everywhere. Just think about the graph. So we'll use our closed interval method. Our first step is to calculate f prime. That's going to be 1 minus 2. The derivative of sine x is cosine x. And 2, we need to find where f prime of x is equal to 0 or undefined. Again, this derivative is continuous, so f prime will never be undefined. So we're just worried about where f prime is equal to 0, and that's often the case. This would mean 1 minus 2 cos x is equal to 0, which is the same as saying 1/2 is equal to the cosine of x. And then it's up to you, in a sense, how you solve equations like this. You can use the inverse cosine function to help you out a little bit. But I encourage you to think in terms of the unit circle because the inverse trig functions have the associated domain restrictions, which can get you in trouble. So if you're looking on your unit circle, where is cosine equal to positive 1/2? Well, okay, here's positive 1/2 along the x-axis, the horizontal axis. And there's two such points. One of them is up here. The other one is the symmetric point down here. The coordinates of these points are 1/2 comma √3/2 and 1/2 comma negative √3/2. This is the unit circle. So the angles associated with those here would be pi/3. And this guy, if you measure him down like this, that would be negative pi/3. If you measure down like this, that would be negative pi/3. But we're trying to pay attention to the interval 0 to 2 pi. So I'm thinking about rotating around like this. All the way around would be 2 pi, which is 6 pi/3. This is 1 pi/3 less, so this is at 5 pi/3. So those are our critical numbers, if you want to call them that, right? F prime is equal to 0. This is pi/3, and this is 5 pi/3. Now there's infinitely many solutions to this equation. I want to be clear about that, right? If you add 2 pi to either of these, you'll get another solution. If you add 4 pi to either of these, you'll get another solution. If you subtract or add any even multiple of pi, you'll get more solutions. But these are the only solutions on the interval 0 to 2 pi.
Excuse me, but wouldn't it be negative 1/2 equals cosine of x?
No. So if we add the 2 cos x to both sides, we get 1 equals 2 cos x. And then divide both sides by 2, we get 1/2 equals cos x. If you subtract the 1 over first, then you'd have negative 2 cos x equals negative 1. And then dividing by the negative 2 will make positive.
Okay, I see. Thank you.
That's all right. No, it's a good thought, but this time we're safe. There will be a moment where I make mistakes like that, though. So I appreciate you looking out. Okay, so we've got all of the solutions to the equation f prime equals 0 on our interval. We know that f prime is never undefined because this is 1 minus 2 cos x, and cos x is happy continuous differentiable everywhere. So we're ready now to compare. We need to compare f of a, which is 0, f at our critical numbers, which are pi/3 and 5 pi/3, and f at our right endpoint, which is 2 pi. Let me just write f of x down here. F of x is x minus 2 times the sine of x. So f of 0 would be 0 minus 2 times the sine of 0. And the sine of 0 is 0. So 0 minus 2 times 0 is 0. Let's see how well we remember our unit circle. F of pi/3 would be pi/3 minus 2 times the sine of pi/3. Oh, because I gave you the coordinates over there, I gave you everything you need. So what is the sine of pi/3? Cos of pi over 3 is 1/2.
3 over 2. Sorry.
Oh, no, don't be sorry. So this is pi over 3 minus 2 times the square root of 3 over 2. And these 2's will cancel. So you get pi over 3 minus the square root of 3. And there are some challenges here, right? If I want to say how big this is, it's not immediately obvious. I'm trying to do size comparisons, but let's see what we have to compare against, and then we'll worry about that. At 5 pi over 3, f is equal to 5 pi over 3 minus 2 times the sine of 5 pi over 3, which is 5 pi over 3 minus 2 times the negative square root of 3 over 2. Again, the 2's will cancel. This time the minus and the negative make a plus. So this is 5 pi over 3 plus root 3. And if I only had to compare these two numbers, I could really easily say which one is larger, right? 5 pi over 3 is 5 times bigger than pi over 3. And then I'm adding something to it rather than subtracting. So just between these two, the bottom one is certainly larger, even without any calculator work. Finally, f of 2 pi is 2 pi minus 2 times the sine of 2 pi. And like the sine of 0, the sine of 2 pi is 0. So this is just 2 pi. So he said between these two, the bottom one is larger. But what about between these two? Or between these two? Anybody have any, without using a calculator, just curious, any thoughts? Of course, we can use our calculators. Say comparing f of 0 and f of pi over 3. You know, f of 0 is 0. So what I'm really asking is this number positive or negative? Right? Bigger or smaller than 0? Any feelings or thoughts on the matter there?
I think it's negative.
Yeah, I think so too. My thought here is that pi over 3 is very close to 1, right? Pi is like 3.14-ish. So this is like 3.14 divided by 3, which is extremely close to 1, right? The square root of 3 is bigger than 1.5. The square root of 2 is like 1.4. That's my reference there, by the way. So like the square root of 2, right around 1.4. It's a good thing to know. So you're taking something very, very close to 1, and you're subtracting something in the neighborhood of 1.5. So this guy I expect to be negative. Somewhere in the neighborhood of negative 0.5, maybe right around there. This guy is definitely positive, because positive plus positive. 5 pi over 3, well, if pi over 3 is in the neighborhood of 1, then 5 pi over 3 is in the neighborhood of 5. So this is somewhere around 5, plus something around the size of 1.5. So this is somewhere around 6.5. And that does leave us a little bit of contention with this one, right? Because 2 pi is also somewhere around 6. So the wise move is to use some sort of calculator tool here. Let's just check it out. So 0 is obviously 0. F of pi over 3 was pi over 3 minus the square root of 3. Maybe I'll just... f of 5 pi over 3 was 5 pi over 3 plus the square root of 3. And then we have 2 pi. Yeah, so we weren't off by much, right? We said this was around negative 0.5. It's negative 0.68, a little more negative than that. We said this guy is somewhere in the neighborhood of 6.5. He's 6.9-ish. And this guy is 2 pi. So 2 times 3.14 is 6.28. So this fellow is a little bigger than 2 pi. And this guy is definitely our absolute min, right? This is the only negative guy. So this was about negative 0.68. All right. Yeah, 68. This guy is about 6.96-ish. And this guy is 2.1, 2 times pi is like 6.28-ish. So the largest of these is f of 5 pi over 3. And that's attained at x equals 5 pi over 3. And the absolute min is pi over 3 minus root 3, which is attained at x equals 5 over 3.
I have a question.
Yeah.
So we were saying earlier that our endpoints, we're not considering them to be extrema, but we're using the 0 and the 2 pi in this process.
So we don't consider endpoints to be local extrema. That's true. But they
okay.
can be absolute extrema.
Okay, cool. Thank you.
Yeah, no problem. The idea there is if we have a monotonically decreasing function or a monotonically increasing function, something that's like always going up, and you restrict it to a closed interval, I certainly can say that the range there has a smallest element, and it's the thing at the left, and the largest element, the thing at the right. So we do need to allow for the endpoints as absolute extrema. And if I'm honest, most textbooks allow the endpoints to be local extrema also, but Stewart does not. Okay. Questions, comments on this one? Okay. There's not a whole lot more to the closed interval method, if I'm honest. It is possible that you can have extrema coming in the form of cusp points, and I do want to look at one of those. It looks like they don't have an example, but I'll grab one from your homework. So when you look at these guys, for example, in problem number 3, at x equals b, we have a local min here. And if not for what was happening at r, this would also be an absolute min. But the function is very much not differentiable there. And we don't have a horizontal tangent line there because there is no tangent line there. So I want to find an example problem where we're going to encounter an extreme value at a cusp point. Those are called cusp points. These do tend to be quite nasty. Let me see. Ooh, maybe they hid them. These show up when you have things like 2/3 powers, an exponent with a ratio like even over odd, or 67. I think will do it. Yeah, maybe 55. Let's apply a little bit of reverse logic. Let me look at the graph of t minus the cube root of t. I'm not sure that will do it. 65 definitely will, but that's a nasty one. Yeah, no cusps here. We're gonna have to do the bad one, aren't we? This was x times square root of x squared. Well, no cusps here either. Okay, maybe you don't have any cusp problems in here. If that's the case, maybe I don't need to beat you up about it. 38 will do it, won't it? No, they're just looking for critical numbers. Okay, well. Cube root of 4 minus x squared. No, no, nothing there either. All right. I'll ease back on that then. I will not push you there because I can't give you any homework with that. So the place we're going with all of this is we want to try and find, we want means to sketch the graph of a function by hand. And that's what 4.2 is all about. You see there's one or two problems in there where they say, sketch the graph of a function with this or that feature. And the idea is that once you just draw a graph, you don't have to be thinking about any algebra. But then once you look at that graph, you want to be thinking about what the derivative could look like, or at least what the graph of the derivative could look like. Before I let you go, I need to write down just one definition. There's a bit of terminology that we didn't define explicitly. So a number C is called a critical number for the function f if, and there's a couple things that we need to be true here. First, f of c must exist, which, i.e., c is in the domain. Of f. And then the other thing is the condition that we discussed in the closed interval method, which is that either f primed of c is equal to 0 or f primed of c is undefined. And to illustrate this, well, no, see, you don't need to worry about custom forms, but why would we worry about this in the definition then? Sometimes Stewart's authorship boggles the mind. If you're hunting for critical numbers, if a problem just says, find me all the critical numbers for this function, then you'll do the normal stuff that we talked about in the closed interval method. You're going to take the derivative and set it equal to 0. You'll also be looking for anywhere that the derivative is undefined. If you find such a number, you must also check that it is in the domain of the original. So let's do one of these. And I'm curious, actually. So I do want to give you something fun. First, and then if I do this, yeah, all right. That's what I just making sure. So let's hunt.
Question.
Yeah.
On the exam, do you want us to write an exact value, or do you want us to write it like how you were like pi over 3 plus 1?
So the exact value there would be the pi over 3 plus 1. So I stay away from decimals unless the problem specifically says to give me a decimal. The decimal is like an approximation, but like, pi over 3 plus the square root of 3, that's the exact value. So that's what we want.
Okay.
So let's hunt for the critical numbers. This is all about the derivative. So we're going to take our derivative, which in this case requires a product rule. If I differentiate the x, leaving the x minus 2 to the 2/3 alone, I get 1 times x minus 2 to the 2/3. And then I add that to what I get when I leave the x alone, but differentiate the x minus 2 to the 2/3, which is 2/3 times x minus 2 to the 2/3 minus 1 is negative 1/3. And then by the chain rule, I'd have to multiply by the derivative of the inner thing here, which is x minus 2's derivative, but that's just 1. Way early on, we talked about a trick for simplifying expressions like this, where you've got some term that shows up twice. One of them is to a negative power, and especially if the powers are kind of unpleasant. The trick is to factor out the largest negative power of that term. So I've got an x minus 2 to the 2/3 here, and an x minus 2 to the negative 1/3 here. I can make my life much, much nicer rather than trying to write this as like a fraction, 1 over the cube root of x minus 2, and then have a common denominator. Yuck. I can force factor x minus 2 to the negative 1/3. While I'm at it, I'm also going to force factor the, well, no, I'll just do that. One thing at a time. So I say, this is the piece that's giving me a headache. Let's get rid of it. Let's factor it out. And you go, but wait, this doesn't have that piece. So you can't factor it out. And I say, aha, yes, I can. It's the same as dividing by that. So this is force factoring. If you take x minus 2 to the 2/3 and you divide it by x minus 2 to the negative 1/3, you'll be left with x minus 2. I'll write it in here like this. X minus 2 to the 2/3 minus negative 1/3. Factoring out is like dividing by. I'm factoring out x minus 2 to the negative 1/3. So that means I'm dividing both of these terms, basically, by x minus 2 to the negative 1/3. And here, that's x minus 2 to something divided by x minus 2 to something else. So the rule is when you divide like bases, you subtract the powers. So that's x minus 2 to the 2/3 minus negative 1/3. In the second term here, all that changes is that this factor, this piece is gone. I've pulled it out. So it's going to be 2/3 x left over. And you can verify that if you distribute this term back through, you will get the line above. The reason this is so nice is because this is going to be quite nice. The two powers here differ by 1. That's the consequence of the product rule. So if you take 2/3 and subtract negative 1/3 from it, that's 2/3 plus 1/3 is 1. So this is x minus 2 to the 1 plus 2/3 x. It's a very nice trick for these algebra problems that can get quite unpleasant otherwise. Now go ahead and take that term and stick it downstairs. So this is x minus 2 plus 2/3 x divided by x minus 2 to the 1/3, or the cube root of x minus 2. There are some like terms upstairs. I have an x and a 2/3 x that I can combine. So x plus 2/3 x is 5/3 x. So I have 5/3 x minus 2 divided by the cube root of x minus 2. And when hunting for critical numbers, I'm looking for places where this apparatus, the derivative, is either equal to 0 or undefined. When is a big fraction equal to 0? Well, what do you do if you want to solve some big fraction equals 0?
Set the numerator to 0.
I'm sorry, I couldn't quite hear it. Could you repeat yourself?
Do you set the numerator to 0?
Mm-hmm. Yeah, that's it exactly. So what kind of fractions are 0? Ones where the top is 0. If the top is 0, as long as the bottom isn't 0, then you're guaranteed the whole thing is equal to 0. So I'll say f primed of x equals 0. if and only if 5/3 x minus 2 is equal to 0, I can add 2 to both sides. And then multiply both sides by 3/5. And I get 6/5, right? 2 times 3/5. And f prime of 0, sorry, f prime of x is undefined when the bottom is equal to 0. So I mean, when the cube root of x minus 2 is equal to 0, cubing both sides, get x minus 2 equals 0 cubed, but 0 cubed is 0. So this is the same as saying x is equal to 2. The last thing you need to do is verify that both of these numbers are in the domain of the original function. What's the domain of this function? The way I talk about this in college algebra pre-calculus, I ask, does this function have any red flags? Like, you know, you go on a first date and your date starts talking about how much they hate their ex is crazy, or they hate their mom, fucking red flag, right? There are some things you can look at with a function that are red flags, like variables in a denominator, red flag. Variables under even roots, like variables under a square root, fourth root, sixth root, red flag. There are no fractions, no variables downstairs in any fraction in this original expression. That red flag is not present. Good. There are some variables being raised to a wonky power, so that should get our attention, but this power, this is a 2/3 power. That's an odd root. The root is the third. This is the third root of x minus 2 squared. So no even roots here either. The domain of the original function f is all real numbers, negative infinity to infinity. So both x equals 2 and x equals 6/5 are critical numbers. And critical numbers is, it's just the name for places where extrema can occur, right? That's why we call them critical. They're the numbers that you're hunting for when you use the closed interval method. And you probably saw when I pulled the graph up for a second to make sure I was picking a reasonable example, that this function does have 2 places where extrema occur, here and here. Now, neither one of them are absolute extrema unless I restrict the domain. If I were to restrict the domain to say something like this, now those numbers are the not just critical numbers, but they're also the locations of your absolute min and absolute max, right? Now your absolute max would be right here, which is that 6/5, and your absolute min would be right here at 2. And the kind of purpose of this example is that critical numbers can show up from the derivative being undefined. Extrema can show up at cusps. Right? Questions on the mechanics here? I'm thinking specifically the algebra. Questions about these processes? I think I asked the first time we talked about it, so I won't push. But if you have seen this trick before, the force factoring trick, that's awesome. If you haven't seen it before, practice it. You know, you can run through this problem again yourself, just being, you know, without looking at the notes, and see if you can arrive at this expression from this expression without glancing back over. And it's pretty easy to cook up more like this, right? Just take some binomial, raise it to a fraction power that is less than 1, and multiply by any monomial that is raised to an integer power, and you'll be in a situation where you can apply this trick. In fact, the fraction power doesn't even need to be less than 1, just any rational number. Okay. So that's it for 4.1. 4.2 though is connected to 4.1, and what we're going to be talking about there is increasing, decreasing functions, connections to the derivative. I always refer to this as how the function affects the shape of the graph. Oh, MVT is in between this. We'll come back to MVT. So 4.3, sorry, not 4.2, 4.3, how the derivative affects the shape of the graph. Affect or effect? Oh, this is one of my bad ones. Affect. Okay, yeah. So the mean value theorem is a neat thing. We'll come back to that because it's going to connect to something we do much later in the course. And that's when we'll play with that. For now, we want to stay focused on this issue of like graph shapes and derivatives. The thing you have probably noticed is that when a function is increasing, its derivative is positive, and when a function is decreasing, its derivative is negative. That does presuppose that the function is differentiable. So if we want to state this carefully, we would say if f is differentiable on the open interval AB and f, say it like this, f primed of x is negative on the interval AB, then f is decreasing on AB. And if you turn this around a little bit, so maintaining your differentiability, you could say if f is differentiable on the open interval AB and f primed of x is greater than 0 on the open interval AB, then f is increasing on the open interval AB. We wrote open interval of AB an awful lot of times there, but it's worth it for the emphasis. The textbook uses the symbol capital I and just says on the interval I. There's some dangerous bullshit in there, my friends. The intervals in question here need to be open. Remember in your algebra classes of yore, you're told over and over again that when you tell me where a function is increasing or decreasing, the answers should be open intervals, because at the endpoints of those intervals, even for the nicest behaved functions, the function is momentarily turning around, going from increasing to decreasing, or going from decreasing to increasing. And right there at those turning points, it isn't fair to say you're doing either thing. This theorem, beyond being a test, is also an explanation. You see, it's an if and only if. A differentiable function f is increasing if and only if the derivative is strictly positive, and decreasing if and only if the derivative is strictly negative. If you throw away the differentiability, this is no longer true. But for a function that is differentiable, increasing and positive derivative are equivalent. decreasing, and negative derivative are equivalent. So if you want to figure out where a function is increasing or decreasing, and you know that that function is differentiable, you just solve the inequality f primed is less than 0, or f primed is greater than 0. If f is differentiable, then its derivative will satisfy a certain kind of continuity condition. It's not necessarily guaranteed to be continuous, but it satisfies what's called a Darboux condition. And in short, what that means is that the solution to an inequality like this, a strict inequality, is guaranteed to be an open interval. So f primed greater than 0 is guaranteed to have a solution that is an open interval, and f primed greater than 0 is equivalent to saying the function is increasing. So when we talk about where a function is increasing, the reasonable answer is guaranteed by this theorem to be an open interval. All right. 1,000,001 applications of this thing. Most obvious is tell me where the function is increasing, where the function is decreasing, right? So let's do it. Let's take this guy, 3x to the 4 minus 4x cubed minus 12x squared plus 5, and find the intervals where it is increasing and decreasing. All right. First things first, we need to ask ourselves, does the theorem apply to this function? Well, the function is a polynomial. Polynomials are continuous everywhere, differentiable everywhere. So yes, f is definitely differentiable. Not just on any specific AB, but on all intervals of the form AB. So it suffices to determine where f primed is positive and where f primed is negative. And the good news here is that you can do them both at once. You want to make a number line, or equivalently a sign chart. You're going to be solving a nonlinear inequality. And if that's something that rings with pain from pre-calculus, it's time to go back and master that thing. So, of course, take the derivative. That is 12x cubed minus 12x squared minus 24x. And we want to solve simultaneously the two inequalities. This is greater than 0 and this is less than 0. And the rock star way to do that is to factor the thing, find those critical numbers, places where the derivative could change sign. That's really what's going on there. And then plot those on a number line. So I'm going to factor. There's a common factor here of 12x that can come out, and what's left is x squared minus x minus 2. And that quadratic is x minus 2 times x plus 1. And then we would make a number line out of this set of critical numbers. So we have here the critical number x equals 0, the critical number x equals 2, and the critical number x equals -1. I know we're getting a little bit past time here, so let me just briefly show you how to finish this. This would be -1, 0, and 2. This is a number line we're making for the sign of f primed. And in each of these regions, f primed will remain positive or negative. The only places where f primed can change sign from being positive to negative or vice versa is at these numbers. Because f primed is continuous, the only place he can change sign is at his roots. If you think about the end behavior for this polynomial, This is a degree 3 polynomial with a positive lead coefficient. That means the end behavior for f primed is down on the left and up on the right. So the end behavior tells me that we're negative over here and positive over here. Then you can use multiplicities to say what happens in between. So as I hop over the root at -1, this polynomial will change sign because -1 comes from this multiplicity 1 factor. So I will go from being negative to positive there. And as you hop over the root at 0, coming from this factor, you will change sign because this is a multiplicity 1 factor. And you can verify that what we got over here from our end behavior matches up with the multiplicity rule, because again, multiplicity 1 factor, odd multiplicity, you will change sign as you hop over that. So f primed of x is negative on the interval -infinity to -1, union with 0 to 2, which means f is decreasing there on those intervals or on that set. And f primed of x is positive on the interval from -1 to 0, union with the interval from 2 to infinity. And by our theorem, this means f is increasing there. So you'd say on this set or on the intervals -1 to 0 and 2 to infinity. All right, we have gone a bit over time, so I'm going to stop here for the day. Next time, we will see how this number line game connects with finding mins and maxes. It is quite cool, but I won't push that on you for now. So that's it from me for today. You're gonna have a new homework opening up right about now. And take a look at a few of those problems before we meet on Wednesday. And on Wednesday, we will continue from here. Take care, guys.